Hello, it's Ahmed Fathi, and in this video I'll try to illustrate why computer graphics operations are parallelizable. In other words, I'll try to illustrate why do we need to use a GPU in order to perform these operations efficiently. What you are seeing in front of you is a game I developed using Babylon.js, which is a game engine built upon WebGL. You can see here that I can move this person here. I can also move this tank. I can fire lasers from this tank in order to kill those persons like this. And I can also go here to this ball and I can fire some cannonballs in order to hit this ball. Okay, let's get to the point. If you look at this tank here or this ball here, you can see that it is actually composed of a number of triangles. Let's go into light in order to see this more clearly. This ball is composed of a number of triangles, and each triangle is of course composed of 3 vertices. Actually, all the objects in our scene are composed of small little triangles. That's how computer graphics works. Everything is composed of triangles. These objects are called meshes. So each object is called a mesh. Now, what does this have to do with our GPU? As we will see soon, if you want to move one of these objects in our scene, we actually need to move each vertex of its vertices independently. We will also see that in order to move a vertex, we actually multiply its position components by some matrix. We will start talking about matrices as linear transformations soon. That said, you can see that any scene you will create will be composed of actually thousands or even millions of vertices. Each vertex of those vertices has to be multiplied by a matrix in order to be moved in its proper location in the scene. Not only that, but these operations are actually done many times per second. So each second, if you have a frame rate of 50 frames per second, for example, you multiply all the vertices in your scene by the proper matrices 50 times per second. So if you have 1 million vertices, you will actually perform this multiplication, matrix vector multiplication, 50 million times per second. This is a really large amount of computation, but it is, on the other hand, parallelizable operations which can be distributed among many processors. That's why we need to use GPU. Another reason we need to use GPU in our computer graphics calculations is actually coloring all those pixels on your screen. As you can see, each pixel of those pixels can have a different color. And as you can see also, the colors of each pixel are somehow independent of the other pixels. So if you look at a pixel right here, for example, you can see that the sun that I created in the scene shed light on this part, and so this pixel has to be brighter than this pixel, for example, or this pixel, and so on. Actually, each pixel on its own needs a large amount of computations. We will explore this when we write actual code, and we will write this ourselves. We will see that for vertices, for example, we will be sending the data for each vertex to our GPU on its own as raw bytes and telling the GPU how to handle these. We will also be sending our transformation matrices, which we will talk about very soon, to the GPU and tell the GPU to multiply the necessary matrices with the required vertices to produce the illusion that we are moving in our scene. So what does actually happen in each frame on our screen? To answer this question, we have to investigate the regular computer graphics pipeline. Our computer graphics work starts with designing or creating our objects. You can design your objects in specialized softwares like Blender and 3ds Max if they are complex objects like men, like dudes, like cars, like tanks, and so on. And you can also design your objects programmatically if they are simple objects like squares, cubes, spheres, and so on. We actually start our pipeline by designing these objects in a space called the model space. The model space is a space where each object is considered to be the only object in our world, where each object is considered to be in the center of our world. So for example, if I would like to design a square, I can create my coordinate systems here, my x, y, z coordinate systems, like this, and then create my cube to be somehow right here. For example, this cube is of unit length, so this point, for example, let's say it is half in the x, half in the y, and 0 in the z. This point is half in the x, negative half in the y, and 0 in the z. This point is negative half, half, 0, and this point is, for example, half, negative half, and 0. So now I have designed my object in my model space. After I do all what I want here, I design the vertices, the positions, the colors, and all other parameters that we will talk about later. I want to transform this object into its correct position in my actual game or into my actual world. This is called transformation into the world space. In the world space, for example, this square will represent a house. I want this house to be on the edge of this river, so I have this house here, like this. You can see that this house is translated and it's somehow rotated in order to match this angle, and it might also be scaled to be larger or to be smaller than these parameters here. So this is the model space, and now we transform it into this world space. We can see that in order to achieve what we require, we need three basic types of operations. We need to be able to translate these points or these vertices to their proper locations in the world space. This corresponds to this, for example, and this corresponds to this. So this is translation. We also need to be able to rotate our objects to have the right correct angle we wish. So this is rotation. We also might need to scale our objects to be larger or to be smaller as required. As for translation, we can actually do this programmatically using some for loop where we loop over all our vertices in our rigid object and apply some amount of translation to each vertex of those vertices. If you do this translation uniformly over all the vertices of your object, even if they were 1,000 vertices, you will actually finally have the result that you wished for. The whole object will be translated in the correct direction. Despite the fact that this can work, we actually do not do this kind of for loops in our computer graphics, because as we will see later, we will be able to use matrices to perform these operations for us, and matrices will be much more efficient than these for loops. The other kind of operation we wish to do is rotation. We wish to be able to rotate this object. To understand how can we perform rotation, let's go here and create some 2D square like this. Let's see, create our square like this, and let's say we wish to rotate it to be like this, for example. How can we do this? It's actually quite simple. If you create a vector here from this origin to this point, like this, and then rotate this object by 45 degrees, for example, it will be somehow here, and this point will correspond to this point. Also, if you rotate this vector here to this second point by also 45 degrees, this vector will be somehow here, and you will have rotated this point, and so on. So actually, if you rotate all the vertices of your object by the same or by the required angle, you will finally find yourself have rotated the entire object as you desire. The same happens for scaling. If you want to scale this square to be like this, for example, you can easily scale each vector of those vectors, multiply it by 2, for example, to be like this, like this and like this, and you will have scaled the entire object. So as you can see, translation, rotation, and scale, all of the three can be decomposed to operations on single points or single vectors. And as we will see later, operations on single points or single vectors will be easily done using matrices. So we reach the conclusion that using matrices, we will be able to achieve what we want. In the next video, we will start illustrating how are matrices used to perform these transformations.